Okay, so good evening and welcome to live session 10. So let's start with the today's first problem. So for the first problem, it was asked that which of the following point or points are correct for strategic disconnection of symmetrical molecules. Uh, so there are a few points. First point is starting from a symmetrical precursor. So to explain that, so let's take a symmetric molecule and we will try to disconnect, and we basically will do the retrosynthetic analysis and try to follow that which of the following points are correlating with our strategy, and that's how we can decide the answer. So to start with, let's assume a very simple very simple symmetric molecule. Let's say this type. So it contains a sigma plane, right? Along this oxygen, carbon, carbon, this along this axis. So that's why it's a sigma plane. So although we all know the correct structure should be like this one, so even that also contain a sigma plane between, if we consider the plane to go through this line. So this sigma plane exists. That's why it's a symmetrical molecule. Now, if we do the retrosynthetic analysis, so what we do for this kind of molecules, you can break these ring bonds. So they are called, you all know, RGD, ring bond disconnection. So when we do the RGD, we generate let's say the which kind of precursors we can generate. So one thing is this, and another thing would be this. So here let's assume we make this electrophilic center. So let's have halogens. So bromine, bromine you can think of. And for this case, we need two negative atoms, two negatives actually. Uh, so uh, so this, how we can achieve? We can consider simply this kind of synthetic equivalence, where with this kind of strong base we can abstract this acidic proton, and these are easily available. So when we do this kind of disconnection, you can see again in the precursors or the synthetic equivalence, the sigma plane exists. So here you can see the sigma plane existed, and same case for other one. So with that, you can see in our synthetic planning or retrosynthetic analysis, we are maintaining the symmetry that our target molecule have. So yeah, in many cases we need to have to break the symmetry also for uh, for some let's say advantage over this kind of cases. So but that kind of things are of course there, but generally we always try to maintain this. So that's why starting from symmetrical precursors is always important thing to begin with. So this should be one of the right answers. You can see if this is the starting material, it contains the sigma plane, and same case for this. So how can we generate that? So just from formaldehyde and this kind of thiols we achieved, we can protect the carbonyl groups, and that also contain the sigma plane. So starting materials have the same sigma planes, or you can say that the symmetry element, which are one of the symmetry element which is present in our target molecule. So maintain the symmetry throughout the pathway. So in this itself. So you can see we try to maintain the sigma plane for any kind of disconnection. So this also one of the right answer. And transformation which brings symmetry for non-symmetrical purposes. So yeah, so for this case it's easy, so that's why we can easily maintain the symmetry of this target molecule. But you may face some molecules where there is to maintain that should is problematic, or if we try to maintain that, and so there may be other path available that are more superior to that. So for that kind of cases, so let's assume uh, another molecule from that to be easier. So let's say for this time we have this kind of molecule. So it contain symmetry or sigma field. But let's try to maintain this, and let's see what things can be problematic. So for that we need let's say this kind of thing, or any X means halogen thing we can think of, and here we need negative. So for this case here we are breaking the symmetry anyway, but here we are maintaining although. So but for making this kind of thing is difficult, and these are not so for this case we what we need, so this type of lithiated species, or this type of things. So generating this type of organometallic reagent and handling that is always a problem. So for that case we may avoid this kind of things, as we have a superior retrosynthetic plan where we can think, so that would be more easier to perform than this kind of thing. And one another thing is that we always have that fear of two nucleophilic attacks, which would generate a alcohol, and we cannot maintain this ester. So that is always there. So for this kind of cases, actually we may think of to have some desymmetrization in our molecule, because this kind of transformation would be well known. So that should be the case. So if we have well-known chemistry that from some transformation we can make a desymmetry sized molecule, and easily convert it to symmetrical molecule. So if it is well known, that why not we should be using that. So let's do a retrosynthetic thing. I hope this. So let's say this is our precursor for that. So anyway, you probably in a glance you may think of that how can we do that, because the whole scaffold actually changes in this retrosynthetic analysis. But as we know the Fabre's rearrangement now, because in previous classes I have discussed maybe in countless times. So Fabre's rearrangement is well known. So with Fabre's treatment we can actually do that. So here you can see there is no sigma plane present, as here we have a halogen group which restricts the molecule from having a sigma plane. So that's how we desymmetrize that, and with Fabre's we actually can regain the sigma plane or symmetry element of the molecule. So how we can make that? So it's quite easy. So from, let's say, cyclohexane hexanol and bromine treatment, if we do the alpha halogenation reaction, we can easily achieve a monohalogenated this molecule. So here you can see the sigma plane is present here, but sigma is not present here, so it is uh, non-symmetric non-symmetrical, and it is symmetrical. So how we can use that? So actually this is context of this, so transformation which will bring symmetry to so this should be one of the uh, uh, points that we may consider. So that's why all the ABC are correct, and so the right answer should be D. Now let's look at how this particular transformation we can do. So as I am telling, it's Haberski type of rearrangement. So if we use this particular base, sodium methoxide, what it would do? So at first it would take the alpha proton. That's they are acidic ones. So after that, this kind of enolate would be formed and followed by an SN2 type of attack, which would remove the Br minus. So now you can see after this particular SN2 or elimination of bromine, again we can write the sigma plane. So by this transformation, we transform a non-symmetrical molecule to symmetrical one. So that's how this particular point C is very much useful for this kind of disconnection approaches, and we need to remember that. So now here we all know how the further things goes. So second equivalent of methoxide can attack this, and followed by opening of one of the remembering bond, because they are strained ones, so which would ultimately leads to formation of this 5-member ring. Here we have now a star, and the negative atom, the negative charge is definitely going to be coined with moisture or during workup, anything you can say. So which is nothing but our target molecule, which contains a sigma pair. So that's how these all 3 points are very much correct. So that's why all of the right answer would be D. So so as we were discussing about the symmetrical molecules and symmetry, so let's go through some of the interesting scaffolds which are very much related to let's say designing of small molecule drugs, or very any natural products that contain this type of hormone codes. So where we always follow these few points in our retrosynthetic analysis. So let's start with this. So here you can see we have a 5-5 fuse system, and uh, here 5-5 fuse system, and followed by a 6-member ring also over here. So one thing is that it contains a sigma plane along this. So this gem methyl, so along this plane the sigma you can think of, and so that's why you will see that we will try to uh, uh, this we always try to make this sigma plane available, and if not we always not always sometimes need to do the desymmetrization, but as I discussed in previous thing, that desymmetrization approach is also important, but we need to have a transformation that can make a disymmetric or non-symmetric molecule to symmetric one. So now when uh, we do the first kind of disconnection, so let's see the let's we have this kind of molecule. Now as it is a we can say it is a pseudo-symmetric molecule, as if this keto bond is not there, then and the methyl would not there, then there would be a sigma plane. So that kind of plane only exists up to this 5 member. So that's why when we disconnect the bonds, so we would try to disconnect it like this, so that in one case we have a molecule where the sigma plane exists, and another one is just to desymmetrize or make the molecule non-symmetric. So in that kind of approaches, you can use this kind of disconnection techniques to make this molecule. And again, for this kind of cases also, you can see this from here to here that it is nothing but elimination you can think of. So O is at the H, it's removed as H2, and here they have an N only. So now if this is there, then in this kind of connection they have done, and it was actually published in long back in Jax in 1979. And for this kind of cases, so these are classical examples of 4+2 cycle addition reaction. So that's how they have disconnected that, and they try to make, and they try to have the 6 member ring always. So that's this this 6 member ring is correlated with this, and these two actually are both are 6 member rings. So that's how the symmetry comes into place. So for this kind of disconnection techniques, and again for this case you can see. So in the molecule we have this type of 553 fuse system. So from here to here you can always do this disconnection. So what we have done, so for this part only you can think that we did disconnection like that. So uh, to make a 5 to 4 membering, and as and with MCPA treatment, and it can easily convert it to its ester form. So that's the first disconnection they have done, and for the second case is nothing but the 2+2 cycle addition reaction. So this with this type of molecules we can generate this. So when we do the 2+2 cycle addition here, so at first uh, this kind of approach or attack, it would generate dihalogenated species at first. So here are let's write like that, and so here we are going to have this species, and always these two bonds should be seen because trans 4 membering is not possible. So that's why this thing is maintained. So that's another approach for the symmetric thing. So let's see. So in our target molecule we have two bonds where both two are seen or cis to each other, but we all know in the 5 member rings, so 5 5 system can exist in transforms also, because it wouldn't generate that much strain system if they are anti to each other. So to make sure that two are in C's, so that's why they probably do or contract the ring to 4 member, as the for 4 member always these two bonds are in cis fashion, they can be trans. So having the symmetry element intact in our retrosynthetic analysis is always helpful. So that's one of the reason for this kind of strategies. So that's why they have included this in this particular category. So now we need to just dehalogenate this species. So how we can do that? Just zinc and in acetic acid treatment we can just dehalogenate this chloroatom. So zinc chloride type thing would be generated with zinc, and as the media is very much acidic, in as the medium is acetic acid, so protonation would be a problem. So when zinc chloride type species is generated, it got easily protonated, and two proton can easily be incorporated over here. So that's for this type of disconnection, and that's how they completed this synthesis. And for this case again, you can see they are contracting rings. So here 5 5, so they converted it into a 6 4 system. Because again here you can see the reason for that, because this 5 member ring, here these two bonds need to be cis, and for cis ones we need to have a 4 member ring. So for that probably they are doing like this. And from here to here, how can we do that? So let's say we just protonated this. So if we treat it with H plus, any acidic acidic media, if we maintain at first the H plus, so how it, so this thing would be happening, and here we would generate a tertiary carbocation. So now here methyl, and here we have generated the particular carbocation. Now the which bond would migrate, that would be the question. So the possibilities are to migrate this bond or this bond. So if this bond migrates, so this migration is not so this bond migrates through this, so then we generate a secondary thing, but the strain of the system would be released. But if we do that, so again some 6 5, but one bridget type thing would be formed. So that's why this is not favored one, because if we do that, you can see this bond, if this bond is formed, uh, it would be 5 6, but it should be 1 2 3 4 5, yeah, 5 6 should be formed, but the thing would be bridget. So let me draw it. If this particular bond migrates, so 6 member, but me uh, so let's write it like A and B. So if B bond migrates, the product would be like uh, this thing. So this, here we have the 6 member ring, and here we generate this. So here you can see it's 5 5 6, but the bridget thing is present like there, so that's why it's more strain. But on the other hand, if we here B bond migrates, if we migrate A bond, let's see, if we migrate the A bond, we would generate a system like this one. So all 5 and no digit thing is there, so that's why this would be preferred one. And when we are doing that, we are creating a positive charge over this center. So we, not this center, I guess, this center, because this bond is forming, and adjacent to that, this this bond is forming, so adjacent to that the positive charge is generating. So here, So now when this is done, oh, and here is uh, methyl also, which also helps for it is a 3-degree thing. So now the elimination would lead to this target molecule. So that's how they have done the first disconnection. So from here they have done so here olefination reaction. So with methyl VTIC we can generate this. So the VTIC reaction uh, can do the thing for from here, and here with just 2 plus 2 cycloaddition would lead to uh, from these two bonds. So that's how they have done this connection. So that's all related to symmetry, and uh, all about maintaining symmetry and breaking or not maintaining the symmetry of the molecule in the retrosynthetic analysis, and how we can make an non-symmetric molecule to symmetric one. So for that's some transformation how people have used. So that's quite overview of that. And so let's come into the next problem. So again it's you can see when you have this kind of things, it's nothing but a Fibonacci kind of rearrangement. So let's do the mechanism, and let's see which of the product would be matched uh, with our molecule which we will get after completing the mechanism. So this kind of species is there. Now when you treat with this sodium ethoxide, and this particular protons are acidic, so one of them can be abstracted by the this kind of bases, which would generate this kind of enolines. So now I am doing both operation in the same molecule, but in the real system it will not be the case. It would be stepwise. So let's say if this happens, then no protonation, no proton abstraction would be there in the same pot, or not same pot, in the same species. So this type of dianionic species would be very much rare to the compared to the monoanionic ones. So for the sake of simplicity and doing the things, I am doing that, but they would happen in stepwise manner, of course. So we should generate this kind of species again. So this kind of species may not be generated. So it can be like this species where this thing remain intact, or here the thing form and here bromine demand. So and after stepwise manner it can occur actually. That would be more uh, you can say more feasible, or more easier to happen as a to from this kind of internet. So when these things happens, now in OET can attack and break one of the bonds. Same thing, OET minus attack and break one of the bonds, which would generate a 4-member ring, and this kind of thing. So here it would try to break this bond because adjacent to ester are less stable due to steric hindrance compared to this kind of thing. Now in which treatment with and heat, we will generate or do the hydrolysis and make this kind of thing follow, and as we are heating and followed by decarboxylation. So two atoms of carbon dioxide would remove from the system, and we would generate this particular four-membered ring molecule. So the right answer should be C, and this cannot be the thing, other intermediate, because one so both contraction would be there. So C would be the answer. So if you have any question regarding this, you can ask. Okay, so moving forward for the next problem. So it is a quite easy one. So which of the following symmetrical in nature considered the plane of symmetry? So their plane of symmetry we will try to find in the molecule, and which one have this should be the right answer for. So this is quite easy one. So just we need to look for sigma planes, and if the molecule have one, it would be symmetry. So now for this case, so with this particular plane, we have a sigma plane, and it goes via this carbon atom and this carbon atom, and it contains these two CO2Me groups, and this CO bond also in the thing. And if we just extend this CO2Me, this particular bond to all again would be in the plane of the sigma. So that's how we cut the molecule, and which would be the sigma plane. So it is a symmetric molecule. So for this case, it also quite related, and again you can think this kind of symmetrical or this particular plane which contains this carbon atom, this carbon atom, this carbon, and this, and like this it goes actually. So the plane which contains this CO, this CO, this particular CC bond, this particular CC bond. So that plane would cut the molecule in symmetrical way, and it would always, and it will be a sigma plane. And this is quite related to this. If we remove this other functionalities, it would generate this. So if this have sigma plane, this of course going to have a sigma plane, because it is more symmetric than this. So this would always would again be having a sigma plane. So that's why the right answer would be the D. All of the things would be having sigma planes. Now for this kind of cases, so let's see what they are asking. So they are so this kind of cyclobutane based symmetrical targets. So again, you can see they are symmetric because here you can think of the C2 or here 4. So C4 can be present, and sigma is always there. So sigma plane is here, here, here. So very much symmetric molecule. So many sigma planes are possible in this particular molecule, because you can uh, uh, do the point group determination also. So that would, if you determine the point group, so then you can just calculate the elements, the symmetric elements which that particular point group have, and from that you can see if it contains a sigma plane or not. So that's with another approach if you are having trouble to find the sigma plane. But of course, when you are determining the point groups, you always need to look for the sigma planes. Otherwise, how you can determine that? So if particular point group is given and you are asked if it is symmetrical one or not, so then you can do the symmetric element determination and can easily look for the sigma planes and may comment if it is a symmetrical one or not. So it have a sigma plane, and they are asking so which of the thing would be uh, do we would do to determine this. So 2 plus 2, of course if 4 member is there, so 2 plus 2 is always an option. Now they are asking 2 plus 2 photo cycle addition or thermal cycle addition, or 3 plus 2. So 3 plus 2 are generate 5 members. I hope all of you know that. One of the example would be this year's Nobel, right? So if we have this kind of molecule, so it is 3 centers, right? 1 2 3 and 2. So 3 plus 2, so alkyne as I click, it would generate the triazole, which is uh, that quick reaction. So that's how this one of the example of 3 plus 2, and here we need to have a 4 membering, not a 5 members, so we can discuss that. And now 2 plus 2, so they are asking 2 plus 2 in thermal condition or photochemical condition. So that's the basic of 2 plus 2 cycloaddition reaction. I hope all of you know that. So 2 plus 2 generally happen in photochemical condition, not in thermal condition. I hope all of you know, but let's to remind you, let's have a quick discussion, just a slide. So for 2 plus 2, for any cycloaddition, when we are doing, we need to have a symmetry matching of the homolumo of the particular molecule. So you need to have the symmetry matched. Now you can say this particular, let's consider plus minus, or here you write this field or not field. So when minus minus is interacting and plus plus is interacting, so here the interaction is favorable, because if the reverse thing would be there, that particular interaction is said not to be favorable one because of the not matching of symmetry and many physical chemistry related thing. I hope all of you have read that, but this is beyond our scope to discuss all of the physicalities of this particular interaction. But just to sake of this problem, we know that to have a bond forming reaction, we need to match the symmetry. So this particular bonding interaction should be there from a bond. So now when let's say this is for this kind of molecule, so pi and pi star are there. So for this we have so psi 1 would be this and pi star would be in reverse. So if in thermal condition we need to do 2 plus 2 cycloaddition reaction, so uh, for this kind of cycloaddition reaction, we need to have a homo-LUMO bond formation, right? So one HOMO would be reacted to another molecule's LUMO, and bond formation would be occur. So let's see if in thermal condition we do what would happen. So it is HOMO of the molecule. So this is like this. So let's write it like that, and the LUMO of the molecule would be this one. So when we do this one connection is fine, but here this we need to the this kind of thing. So supra bond formation is not possible. Supra intra we need to do, but we all know this kind of strain system for formation of 2 plus 2, this supra intra thing is not possible, because for that we need to have a very long chain for, let's say, 8-member things. So there only the supra intra thing is possible, but here it is not. So that's why this interaction is not possible in the thermal condition. So thermal condition does not allow the 2+2. So when we apply light, it's new condition. So then the new HOMO would be this. So let's say this is our new HOMO, because it is arrest like this when we applied the H new. And so let's say 50% of our molecule reaches up to this, and another 50% are still in this case where LUMO is here. So now this is LUMO and this is HOMO. Now if we write this, so let's see. So this is our newly formed HOMO, and our LUMO is also having this kind of thing. So now you can see supra is here or easily possible, and the bond formation reaction will be happening, and that's why each new condition is needed for this 2+2 cycloaddition reaction. So that's all about little photochemistry, and I hope all of you know for 4+2 cycloaddition we need heating conditions. So they are, if you draw the thing, you would end up with homolumo thing. If you end up in such a way that only thermal condition would allow to form this kind of supra bond over the photochemical condition where supra and you would face, and that's how things should dictate. So here I can briefly describe that also. So now if we do the 4+2, so there we have dynamic systems, right? So this kind of cases. So here if you do the write the orbitals, so 4 things will be possible. So for uh, for psi 1, everything, let's say, it's like this. Psi 2 would be going to have one node. This is psi 2, and for psi 3 is going to have 2. So here we are going to have the node. So this is psi 3 and psi 4. We are going to have 3 nodes. So cipher is like this. Now if we fill up the electrons, so we going to have 4 electrons. So when we fill up that, so 1 2 3 4, so this side would be our HOMO and side 3 would be the LUMO. Now if we do the energy matching thing, let's see. So let's say side 3 is the LUMO, so that's why I am writing this here. So when we write the side 3, it is like this. Now so as it is HOMO, or sorry, LUMO, so for the dinophile of the double bond, it going to be HOMO, right? So if HOMO we write, here you can see the supra interaction is there in thermal condition. So that's how the 4 plus 2 occur in thermal condition. Now if photochemical condition we use, what HOMO we have generated, so there HOMO is like that. So now if you write the, so this is HOMO in the photochemical case, and this is going to be the LUMO. So there you can see the interaction would be supra intra. So then the photochemical condition would not allow this bond formation. So then only that's how the 4 plus 2 would be only in thermal condition. Now coming to this problem, so this transformation can be viewed as, so intramolecular intramolecular 2 plus 2. So here you can see the two double bonds are there, and when we from this particular two bonds and make the four member ring, this four member, so 1 2 3 4, this four member ring is just this particular four member, and we are doing in the same molecule, so it is intra. So easily you can solve this. So 2 plus 2 photocycle addition, just we have discussed. 4 plus 2, so it is not a 4 plus 2. So inter one, if let's say two molecules, so if four member ring be formed here, and here we going to have this particular same moiety, then it would be intermolecular. So it is, as it is happening in the same molecule, so it is intra. I hope all of you know that, and actually, and so it is a very easy one. But one thing I want to discuss here is the completion of the synthesis actually. So this is for a particular synthesis actually, where it is taken. So from here, let's say we have done what, 2 plus 2. Now we just do the deprotection of that. So all of you know that. So in presence of acid, one of them would be protonated, followed by this kind of elimination, which would lead to formation of this thing, particularly like this. Now each two atom can attack neutralize this, and followed by again elimination of this O bond, which will generate the keto functionality over here. So this is things. So after this ketality protection, you would generate a molecule like so bromine is there, bromine is there. So this kind of molecule we are going to generate now. Favorsky reaction, as we have discussed actually, we going to do that. So we are using sodium ethoxide in ethanol. So same kind of thing. This proton abstraction acidic from the Favorsky thing actually. Then this bromine elimination. So then it would lead to. Let me just write it over here. So when that happen, this kind of thing will be forming, right? This kind of thing, and bromine would be uh, leaving from this system, and this kind of cube gonna form. So now let the cube form. So this kind of cube system forms, and it have this functionality, and here this functionality is remaining. So now OET minus would attack here and broke any of the bond, any of these bonds, let's say this, and it would generate diester type molecule. So here CO2 and here CO2. Now same, you can see the same operation we have just done in this kind of thing. CO2 it is there. So from here what we have done, we just treated with sodium hydroxide solution and heated. So it basically hydrolyzes the esters to acid and followed by carbon dioxide removal, which would generate this molecule. So just few problems back, one two. So we have done this. So here just you can think of the same way. So behind things are there, but this formulating have this anti to diesters. It is related to like this, and if we do the same treatment in a which followed by heat, the same way to carbon dioxide would be removing, and it would form a Cuban type moiety, right? So that's how we can generate this kind of structurally integrating molecule, which are not uh, naturally occurring, but for synthetic purpose. So for let's say some material designing, or uh, just for study, we can just for academic interest we can make. So what would be the strain, what would be the bond energies of this carbon carbon bond. So for this kind of an academic interest, we need to make this kind of molecules, then we can use this kind of this particular strategy favors. So Faber's rearrangement comes handy for this kind of molecule preparation. So I hope that this probably previous or my our life lesson 9 we just discussed one particular synthesis by Govardhan Mehta, which is Garurin, which is also based on this particular Fibonacci rearrangement type strategy. So Garurin also. So Garurin, I hope all of you remember the structure of Garurin. Let me write that also. So let's clear some part. Say clear this. So Garurin structure is like it have two 6-member rings. So here actually is this. So this kind of thing is Garurin again quite related to this particular family of compounds, and they are what they have done. So 6-member ring. So here you can see what we have make actually 5 to 5 member rings are there. Then with Fibonacci we just contracted ring to 4 members. So again in the same strategy here it is 6 to 6 member rings are there. So if we started with a 7-member ring followed by ring contraction, we can generate that. So that would be quite in the similar fashion actually. Here the thing would be the same like this. Same way, just so here 6-member ring would be there. That's it, this kind of thing to 7 members. I hope all of you can understand that. kind of thing, and the keto functionality would be here and here. Here, so it would going to have a 7-member ring. That it is 1, 2, 3, 4, 5, 6. So just have a extra. So the extra thing would be like this, and followed by debromination the same way. So in the same way, so just think of this 6 is going to have a 7-member ring like this, and from there we can generate that. So in the same way, we can generate lot of this type of theoretical or molecule where we can use this particular Fibonacci reaction in very efficient fashion and do the ring contraction. So yeah, here you can see they have just completed the synthesis from this to this. So just what we are discussing. So here you can see the first Fibonacci they have performed and contracted that, and for then they have they're going to need a reprotection of this. So let us see what they have. Sequential removal of ketal functionality. So yeah, ketal functionality should be removed at first. So all have the, yeah, first thing is the, and then this for Fibonacci and Ricard. So it would be the right answer. So just pick the previous one. We have discussed this. So how we would perform the um, uh, that ketal protection followed by Fibonacci and decarboxylation reaction. With Wolf Kishner, so let's look at the other things. What? So if B is the case, so now we have done the first ketal protection, which will lead to this, followed by they are doing a Wolff-Kishner reduction. So if we do the Wolff-Kishner reduction here, what we do, it just reduce the keto, and it introduced to hydrogen atoms like this. The reduction thing. So I hope all of you know the reagent, hydrogen hydrate and QH. So here very high heat we need, so 150 degree to 160, 70. Sometime you're going to need greater than, because it is a keto, not aldehyde. So this kind of heating may also be needed to perform this kind of reaction. So their chances are debomination may also happen in this high heating. Uh, so this should not be the case, because in contraction we can do in this particular reaction condition. So I hope all of you remember the mechanism. Just let me quickly give you that. So hydrogen hydrate at first do the hydrogen formation, then in presence of base it would make this kind of thing. So first this will be formed, so this negative charge will be going by water, so protonation will be occurring over here. The first protonation followed by nitrogen nitrogen bond formation. This thing now again KOH can take up this, make it in negative, followed by in triple bond formation, and again carbon nitrogen bond disconnection followed by its proton abstraction, lead to formation of this, and nitrogen will be removed from the system. So this is the mechanism. So next thing is this one, Mojingo reduction. So again, Mojingo or Wolf Kissner, this kind of reduction just make this functionality to this automation. This thing it can do the configuration which Saborsky can. So this cannot be the right options for that. So Mojingo is this particular reaction, and you can see that it is quite related to that ketal formation. So at first with these two thiols, this particular thing would be forming, and in presence of H2 gas and nickel nickel media, just reduction would be there, and it would be two proton you would introduce. So just a reduction, not a ring contraction. So this is the Mochingo reduction, and this is all for the sixth problem. Now coming to this. So this particular thing is viewed as exploration of Michael or enolate alkylation, or exploration of both enolate alkylation and Michaelization. So let's do the mechanism. Let's see if we disconnect that. This one and this one we need to disconnect for this. So it should generate these two functionalities actually. You also see that one of our first problems, it is said that for the disconnection we need to maintain the symmetry, and here it have a sigma plane. So this thing just problem back we discussed. So when we do the retrosynthesis we always try to maintain that. So that's why you can see after disconnection we have generated this molecule which is also have the same sigma plane, and here also we have generated the synthon which is symmetrical. So this kind of thing we have generated. So here we need a positive, also here we need positive. So possibilities are there. The synthetic equivalent from of this molecule can be this dibromo thing, but it should be quite complicated to make, I guess. So that's why then we make a further some we perform some desymmetrization, and we have this particular synthetic role. So its role basically is the same. So after the elimination of bromine, and it would generate the same this synthon, which is basically the symmetric one. It contains sigma pair. So now if we do the mechanism, so at first we have this molecule, right? So let us write that this molecule, so negative charge or inhalation we at first generated. Then let's say it is a symmetric molecule, so anywhere you form the inolate, not an issue. Now it would react. So at first it would do Michael or normal alkylation. So anything you can do, you would end up with the same thing. So after this first bond formation, you going to have a molecule like this one. Here you have this particular double bond. Or if you do the reverse thing here, after this addition, here you are going to have this bromo thing for alkylation. Now again second annulation followed by Michael addition would lead to formation of this 6,6 bicyclic system like this. So here you can see first is this alkylation, and then this 1,4 methylation. That's why one of this alkylation methylation both are explored in this particular thing. So that's why the right answer would be this. Coming to the next problem. Again, so this particular problem is can easily solve actually. So the options they are asking some reaction sequence. So first thing is diagonal transfer. Oh, so if someone join, please mute actually. Uh, Having some background noises. Yeah. So at first the diagonal transfer reaction. So I hope all of you know. Can you please mute actually? Okay, fine. So this but the first reaction would be the diazo transfer reaction. I hope all of you know that. So at first you have this type of active methylene species where this particular carbon atom, it have these two acidic protons which are doubly activated by the keto system. So in the this sequence I am going to discuss where it is quite similar to that. So there it is keto one, and here it is ester. So that's why this particular this methylene group is doubly active. So active methylene compound, and so in presence of diethylamine or any kind of base you can use. At first this enolate formation would be there, followed by we need a agile transferring agent, which is this kind of thing is generally used, and it is just the toluene moiety, so benzene ring and methyl, and is commercially available. And here you can see this particular resonating from this particular nitrogen is electron deficient and prone to have a prone to attack, and this is electrophilic center, and that's how this particular annular at first attack this nitrogen atom and it generate this particular molecule. Now this is nothing but we need to do just some elimination to have this in. So now what they have done, so in present it is we are having a basic condition, so that's why this is an acidic proton which can be removed, and again we can form the enolate. Now when we form this particular enolate, this and this come here, this and kind of this kind of mechanism. So here you can see just this nitrogen nitrogen bond we are disconnecting, basically nothing else. And here we are having this at into species, and which can be in any of these resonating from. So this would be the preferred resonating. So we what we did in this particular reaction sequence, so we make this molecule to this particular molecule. Here we have N. So This is in the reaction condition. This is basically the source of this particular type of carbene actually. So from here, after removal of nitrogen, we can easily generate this particular carbene. So which is the source for 2 plus 1 plus 2 or 2 plus 1, anything you can say, cycle addition reaction, uh, by which we can make this type of triple bond. So that's the thing why we introduce one azide group over here. So here you can see at first this not azide, so diazo actually N3 is there and azide. So diazo. So at first with this diazo transferring agent, we are going to generate a molecule like this. So here we have into this particular thing we are going to have. Now this heating condition or any other reaction condition we can use to make the carbene over here, and so or base. So many things can be utilized for the carbene generation over here. So when carbene is generated, so after carbene generation, so and this is the double bond, with this it only can attack. So now here you can see this 3-member type ring formed like this. So it is just because two carbon atoms and one carbon atom. So 2 plus 1 center. So this is, that's how the 3-member ring is forming. So it is that's why the answer is A actually, 2 plus 1. The 3-member ring we are forming. So if 2 plus 2 we are going to form a 4-member ring. It is not the case over here. And 3 plus 1 again we are going to have a 4-member ring, but 3 plus 1 I think quite rare, and he didn't recall anything of 3 plus 1 actually. So anyway, the for this case it is 2 plus 1, and we are going to generate this particular 3-member ring over here, and rest of the things are like this. So that's why it is this particular reaction sequence. At first we need to have this diazo transferring agent with the have the diazo, and then followed by carbene generation and 2 plus 1 reaction. So that's why this A would be the correct reaction sequence. So this is the diazo thing. And coming to the next problem. So with sodium hydride and TBS chloride, and it is used in one equivalent. So sodium hydride is base and not a nucleophile. You all know, I think. So here in this context, you can just discuss one thing, that why sodium hydride is only act as base, not as nucleophile. So for when we need H minus as nucleophile, what we use? We use this kind of species, aluminum hydride or NaBH4. Never so called are nucleophiles. But H minus, when we need to use as nucleophile, we never use sodium hydride. So why is that? For sodium hydride, it is just this. So this kind of interaction is there, and it is ionic. So H minus only have s orbital. So s orbital does not have any directional property. So that's why it cannot be act as any nucleophile. Whereas when we use this kind of thing, so they are, yeah, so this kind of things exist, right? So here it is hybridized. Not only S, it don't have only S character. So with aluminum, it can probably SP character, some not pure S character is there for this particular thing. So hybrid orbital for this kind of cases. So here we have directional properties and it acts as nucleophile. So that's one of the basic things actually. So why sodium hydride it cannot act as nucleophile, it only acts as this. So that's the reason. Now coming to this current problem. So when we use the sodium hydride, so what would you have? It do it abstract one of the protons. So this can be formed or this can be taken. So same thing actually as it is a symmetric molecule. Now followed by TBSCl. So TBSCl, I hope all of you know TBS group. What is this? So this is particularly this thing is TBS. So uh, uh, chart, uh, tertiary butyl group is there, T-butyl and so TB butyl silane chlorosilane. So that's the naming actually. From here it came that TB butyl group. And when we do that, so we all know that silicons have higher affinity towards this kind of molecule where the electronegativity of this atom are very much high. So that's why oxygen can attack this and remove this. So electronegativity factor dictates over here. So electronegativity, we all know that fluoro, then oxygen, then fluoro. That's why oxygen silicon bond is formed over oxygen silicon fluoro, and when we need to the deprotection we use this F minus. So there we use this kind of species actually. This kind of species are used, or yeah, any R4 you can long chain alkyl group can be used. Now so after this by by what we would be generating this kind of. So as one equivalent is specifically mentioned, so that's why it would be uh, this one particularly one mono-TBS protected ether. So only one would be there. So I would not be the place and two mono, two not two. So it can generate the streamer cannot be generated because one thing is that. So this is one of the molecule, and let's say another case this is getting attacked. So then the product would be like this one, right? So if we do the nomenclature, so 1 2 3, so it would be R. Again here 1 2 3, it would be R. So R, R. So yeah, here no issue actually. So that's why it would be 1. So B would be the right answer. And for this case, I think the thing would be different. So, yeah, here racemization would occur. So for this case again in the same thing, so one equivalent, one equivalent. So any of the two probabilities are formation of these these two are possible, and another would be this. So these two possibilities are there, but one thing you can see, these two are actually enantiomers. So, but this is a chiral one. So let's say it in the polarimeter it have a positive rotation. It is a chiral molecule. But when we do this particular treatment, but in this particular treatment, the chiral centers we do not touch, so they remain in unreacted. We are only reacting over this. So as our previous experience, we know that if the chiral centers we are not interacting, so then in the molecule the chirality should be intact, and a chiral molecule would always generate a chiral molecule. But for this case, what is happening due to its structural features, you can say, uh, although we are not interacting in this particular chiral centers, we are only playing with the oxygen and proton, oxygen and hydrogen bond, but also we are actually generating two enantiomers. So now after this reaction, the product would be racemic. So if we measure the polarimeter, it would give a value close to 0, where it going to have a higher value. So this is one of the interesting observation for this kind of cases, where although we are not reacting or touching the chiral center, but then also we are racemizing the compound overall. That's why the right answer would be this, two enantiomeric monobenzyl peptide. That would be the case, and so that's the today's last problem, I think. And but here it is not changing, I guess. So here, if we try to draw that, so that so it is actually, if we draw it in this particular fashion, then we would generate, it would be below, which this one molecule we generate and another molecule would be uh, another molecule would be here OH, and here OTBS. So now, so these two not are enantiomers, they are homomers, because if we do, let's say, 180-degree rotation, in particular this axis, we just rotate this molecule, we would generate this particular molecule itself. So this molecule is chiral, but here if we are, let's see, if it has plus, so it would generate either plus or minus, so depending upon the nature of the molecule, but the molecule would be chiral, not racemic, because here you can see these are two anti positions, so that's why the thing would be chiral. But if, let's say, we start with same or cis molecule uh, like this, then it would generate a plus minus or racemic thing. So this is that, this like this molecule. So these two things are there. So which are completely based on the stereogenetic property of the particular molecule. So we always need to have this kind of understanding of this particular molecule, because when we would do the transformation and measured this optical rotation, we need to remember this particular thing, because here the thing that we are not touching the centers, but decimization is there. So that's regarding that. So I think this one is previous from the previous class. So up to this is the today's new problem solving session. So this is all. So if you have any question, you can ask anything about the lecture that is recorded, or today's topic, any of the topics, or otherwise I would discuss one of the total synthesis, method of total synthesis, where we have used this kind of reactions that we learned. So I guess no questions then. So let's move forward for a total synthesis real life research, how people are using this particular reaction condition, these strategies to make this kind of structurally very much complex looking synthesis. So let's say this ambiguin H. Let me have so this particular ambiguin H is our target molecule. So there are many ways we can start the retrosynthetic analysis and do the disconnection. But first, for the structural features, you can just see this particular moiety. So it have a indole moiety followed by it has a this reverse phenyl group. So in nature how it is made. So here you can see this particular indole, and the phenyl or reverse phenyl can be having from this particular isoprene units followed by this kind of it is probably mm, so diterpene or tetraterpene type of things which are naturally occurring. So from that the nature is making. But when we make this kind of molecule, we what we do or what people do, the protection they use protection group chemistry. Otherwise, the controlling the reactivity of these particular centers may seem very much difficult. But for the sake of this particular paper, they probably do not use any kind of protecting groups, and yeah, this work. So their work is completely protection group free, and that's turned out to be the selling point of this particular research. So no protecting groups, no enzymes, and they still able to maintain the natural reactivity of the centers. So what they have used? They have used this particular molecule, an indole, and this kind of prenyl group thing, prenyl alcohol. If it is OH over here, so that's the thing they have used to complete this their molecule. So let's look at their electrosynthetic analysis. So this is their target molecule, ambiguin H, and from nature they have seen that quite related to this hepalindole U. This is also a naturally occurring molecule. So of course, if nature makes it come from the same pathway. So from here, nature just incorporated one isoprene unit in this way, which is the reverse phenyl group, and which lead to this ambiguity. So this can be formed from this. This is also NCS, and here you can see if this here actually the indole ring, this indole ring is this indole ring is here, and the three position is connected to this particular six member thing. Here also this three position is connected to this six member thing. This group is there, but also this group is considering to this, and this two dimethyl thing is just this, because after reduction, let's say protonation is there, so dimethyl thing followed by this positive charge, and which uh, can be attacked and make and do this particular cyclization. So this cyclization would lead to this six member formation, and here the thing is that NC and NCS. These things are just different for this particular natural product. So in this way, from the isolation paper itself, if we look close and analyze things, it generally unravels the nature's retrosynthetic pathway, how nature makes, and in the lab people try to mimic that, and that's the research work that's going on for decades, you can say. So another naturally occurring molecules are like this. They are also quite related to that, but you need not to be bothered with that much molecule. So let's just discuss these two, and let's see how they have synthesized that. So in the first slide itself, they from nature we know that this should be one of the partners, and this is just a uh, 4 bromo indole and just indole, naturally occurring things. It is also a naturally occurring molecule, and they have made this also from commercially available molecule. So at first what they have done, so LH MDS and copper 2, and here they have put bromo 2. So first in presence of HMDS and copper, they just from this particular bond formation reaction they have done. So this particular C2, this alpha position of this carbon atom, and followed by the bond formation of those 3 positions. So this bond formation reaction at first they have done in presence of LHMDS and copper 2. So after this bond formation reaction, what they have done, the palladium to catalyze this particular bond formation reaction. So here it is bromo. So in presence of palladium, so at first oxidative addition would be there. So this kind of species would be forming. Then the migratory insertion. So at first let's say this, then migratory insertion would form this particular bond, which is the six member one. So that's how this six member bond is formed, and they have generated this particular molecule. Now this is a reducing agent of alcohol. So basically they have done that, and so with this H minus, one of the H minus would approach like this. So this proton, this hydrogen atom is got, and with this particular reaction condition, COCl2 and acetic acid thing, they introduce this NC bond. So let's see, I have so these things just I have discussed. So at first the oxidative addition of this, then halogen thing is there, followed by this migratory insertion, and alpha hydrogen or beta hydrogen elimination reaction would lead to this. So this I have just discussed. So yeah, so how the CDMT NMM thing, this is this, and this is how they have synthesized the molecule 7. So from here actually they do this thing, followed by NC group incorporation. So yeah, this thing actually CDMT and this. So that's how the CN group they have incorporated, and NC thing with COCl2 it's easier. Now after that, this is actually this hepalindoleu, one of the one of the natural products that they have synthesized. Now from here, what they need to have a reverse vinyl group incorporation. Need to do a reverse vinyl group incorporation over here. So for that they have done this. So prenyl 9-ppn is just this. So 9-ppn you all know, with cycloocta 1,5 cyclooctadiene and for NDMS we can form the 9-ppn thing, and with 9-ppn and this particular alene we can generate this prenyl 9-ppn thing. So the structure would be here. Let's say you have the 9-ppn and two 6-member rings and CH2 and this with alene. This reaction will be done, and this is actually 9-ppn prenyl group. This particular reagent, plain 9-ppn. Now at first what would be happening in uh, that butyl hypochlorite case? So this is actually source of Cl plus. So here you can see the Cl plus, how Cl plus incorporated in the system. So chlorothene came, and here actually this particular attack is there. So these these three position attack over here, and it the C minus abstracts the chlorine plus and generate this kind of residue. And with 9-ppn thing, this particular species is generated. So nitrogen boron bond is forming, and nitrogen would have a positive charge and this. Now after that, two position is susceptible to attack. So for neutralization of these two positions, this particular reagent is used, and this actually for TANISAP this reaction protocol, actually this reverse vinylation thing. All all people are following that particular protocol. This start butyl hypochlorite followed by pyridine 9-ppn. So now this boron carbon atom bond breaks and followed by this carbon carbon atom into position. So this R is nothing but that reverse vinyl group. So this start vinyl it's nothing but this particular group. This particular group incorporated like this. And here we have boron nitrogen bond. So generally in reaction condition they tend to grow followed by ACL removal when normal indole thing is there. But here you can see some complication over there because of the presence of the CN group. That's why this particular they can isolate this particular intermediate. But for the reaction we need to have this. So to regenerate this, so what they have done, H nu mediated triethylamine treatment. So in H nu what happens? So that forms radical over here. So this particular carbon carbon atom tends to break because of the strain, or the particular this carbon carbon bond energy is lower. That's why this homolytic cleavage is possible, and after that this radical is formed. And here you can see this particular NC bond is there, and this particular radical can extract this particular hydrogen followed by this so when this abstract here, so again radical radical combination would generate this double bond, and here this thing. So here when this particular species is formed, they have seen that this particular chloroelimination is very much possible to regenerate this NC group, and when this forms, this chloro minus can attack the boron, which facilitates this boron nitrogen bond cleavage. So when this bond cleaves, this N minus will be neutralized by the proton which is available in the system, and it will generate this ambiguine H. So that's how they have completed their synthesis. So here you can see there is no protecting group, and without any protecting group they have use some basic chemistry, right? So the carbon-carbon bond formation reaction in presence of LHMDS and copper, then palladium based this beta hydrogen elimination. What palladium do actually? Oxidative addition, migratory insertion, beta hydride elimination, and followed by reactive elimination. So that chemistry in this step followed by on reduction and NC group incorporation with this particular type of reagents. So reagents, when they are written in this type of short form, you may feel it uncomfortable, but just look up in the net or anywhere for the full forms and to the mechanism, it would be easier. So nothing new over there. So after that, this particular reaction condition, it is also well known in the literature how to incorporate this particular reverse phenyl group. They just follow their protocol and followed the and completed the reaction. So that's the thing about this kind of research. So go through the literature, what kind of known reactions are known, and based on that and knowledge from the nature, how nature is making. So we need to combine this and we try to mimic the nature in the chemical way in the lab. So that's how the product synthesis goes, and they have successfully done that, and it's done in 2007, and look at it's published in Nature, and by the the Baran group have done that, and so quite a popular group. Probably some of you know him, the Phil Baran. So this is for this ambiguous age total synthesis, and some optimization thing is there. So indole carbon, that first step, this this LHMDS, this thing. So for that they have done this. So let's look at how they have optimized that. So that's how the reaction medium goes. So base, for that case what they have used, LHMDS. So this is actually base. So if all of you know, lithium and silicon mediated base actually, LHMDS. Quite a common base in reaction in the laboratories. So when the base is used, what base can do in the indole? So it had proton, so proton base would abstract and would generate this, and again it is also negative. Means acidic protons, as it is alpha 2 carbonyl. So there we also can generate the enolate. So now negative negative. So now the beauty of this particular reaction, because if we do this thing, so here what it is negative and here it is negative. So how we can combine that? Because if we need an attack, we need to have a one carbon electron rich and another should be electron deficient. But here we are seeing both are carbon, both are electron rich. So how we can form this one? So for that they have their methodology, actually they have discovered that. So then only then the oxidant come into place. So that's why what oxidant uh, they have used? So copper, right? So copper 2 can go to copper 1. So itself what it is doing, it is reducing. So when it itself is reducing, what it tend to do, it will take a electron from the system. So from where it looks that electron, so from this uh, negative atom, or from this carbon negative, or from this carbon negative, from one of them or from both of them it can do. So that's their blueprint, what kind of oxidant they can use. So that's where they do the optimization thing. So here you can see with LDA base they have tried, and with LHMDS they have tried, and what oxidant they have used? Coppers and iron, Fe. So now after they have tried these five entries, means five optimization they have done. So at first when they are doing with Fe and LDA, they are getting product, but you can see the yield is very much less, 15%, very very much less, so that's why they need to optimize. And with this particular condition where LHMDS is the base and copper 2 is the oxidant, and in the temperature is -78 degrees, there they have got up to 53 to 70, so up to 70% BRSM, means based on starting material recovered yield they achieve 70% yield, and from this particular carbon carbon bond. So this kind of unplug thing, that two carbon atoms are negative but we are forming bonds with help of radical generation. So that's also done by Baran, and it is published in JAX in 2004, and based on that this particular methodology they have utilized in first step itself, which is to the nature 2007. So here you can see the same reaction condition in HMDS and copper they have used to form this particular carbon carbon bond. So that's how they utilized their methodology and completed this particular synthesis of ambiguous H. And another thing is the optimization of 9 to 10, right? So this particular thing, the palladium based carbon carbon bond formation, it's again well known chemistry, and but although it's well known, we need to do this type of optimization thing, which condition would suits most to do the particular reaction. So here they have used this Herman's catalyst TBAB triethylamine. So this is actually Herman's catalyst. This is the active species of the molecule, which is nothing but you can see the palladium species followed by this particular these two are same, this particular ligands, and this is nothing but acetic acid residue CH3O O minus. So in the particular this kind of, so this particular thing is the conjugate base of acetic acid is used for this particular thing. So this thing, three things are combined to make this particular complex, which is actually Hermann's catalyst, and it is a Heck type, of course, Heck type annulation reaction, which is and they have the catalyst loading is 10% of palladium, and base is used as trithelium. So in 80 degrees centigrade DMF they have done the optimization and get up to 65% over that step. So that's how they have completed the synthesis of ambiguous H, followed and mimicking the nature. And in the same related compound they have published in that paper itself. They are so today we are not going to discuss that, because this is I think enough for today, because this is quite new things for many of you, how they have optimized this particular carbon carbon bond formation reaction and use this. And this is Heck type annulation, quite well known, then reduction and third butyl hypochlorite inverse. So you can see only five six steps they are achieving this particular complex this molecule. And the one of the selling point is the no protection group is used. So that's the total synthesis of ambiguity. So regarding this, if you have any question, you can ask, or today's session we can close. Actually, it's almost 8. So if you have any question, clarification, you can ask. Okay, seems like no questions there. So whoever have joined earlier and remained until now, thank you. And so it's going to be in YouTube also. So there you can rewatch if you miss something, and if you have any question, just pin a comment over there, or you can mail me also. So thank you for joining. So this is the end of live session 10. So we going to have two more live sessions, followed by one summary class if we need it. So let's see how things goes. And thank you all for joining. So we will meet in next Tuesday, same time, 6 to 8. Thank you.